The 1 microparticle was found to have a terminal velocity of 13 micrometers per second. Once again, assuming streamline flow, Stokes' law was applied and the trapping force for the 1 micron particle was 0.123 piconewtons. So what does the results mean? Based on Stokes' law, the trapping force is proportional to the radius of the microparticle. The experimental result matches this relationship as the trapping force of the 3 micron particle was larger than that for the 1 microparticle. But why were the microparticles dislodged at terminal velocity? As the flow velocity increases, the drag force increases, causing the microparticle to deviate slightly from the equilibrium position. At lower velocities, the gradient force will attract the microparticle back to the highest intensity point. However, when the flow velocity is greater than terminal velocity, the drag force exceeds the maximum optical trapping force, dislodging the microparticle from the optical tweezers. Therefore, the maximum optical trapping force is achieved at a fixed laser power that corresponds to the viscous drag force at the terminal velocity. Optical tweezers can be modeled into a spring by the Hooke's law F equals to negative K. For 3 micron particle, the spring constant is 1.58 times 10 to the power of minus 8 Newton per meters. This means that the trap is stiff and rod-like. Thus lead to a higher conservation of energy as less amount of force is required to move a certain displacement as compared to a spring-like trap. After the experiment, there were a few things to note for improvement. Due to the size of microsphere, there is a difference in trapping force, thus higher terminal velocity were required for the distance. For better comparison, the fixed distance for 3 micron